today's topic is basically what I want to do is to do some non-trivial consistency check of this linear person. So this non-isometric code tries to define a map between two different pictures. One is called as the vector picture. I think of it as a picture that is viewed from the point of view of someone who falls into a black hole and goes into the interior. And there you have these two different modes, the left moving mode and the right moving mode. And this is the notation that I'm going to use throughout this talk. And of course, if you're outside, there's a radiation that is like moving outside. That's going to be the area of calculated on. So this is the perspective of someone who falls into the black hole, whereas we stay outside and don't fall in. We'll see this like thing that is emitting radiation. I'm going to call that like E, denoting the black hole. And there is like radiation that is like coming out of the black hole, which would be this R, the same R as here. And we can model this like left-hand side of the picture as some like quantum circuit, starting with some like L, the left moving mode, and some quantum field degrees of freedom, that's psi naught, and little r and large r. And from the outside, what we see is some like unitary process of some quantum mechanical system, denoted by this unitary U, so that this unitary is applied to these like quantum field degrees of freedom and the left moving mode, and outproduces the black hole and the radiation. And what non-isometric code is trying to do is to basically map the left-hand side to the right-hand side. And the way in which this works is very simple. What you do is to simply apply this linear map described in this like this dotted blocks. And you can see that it's clearly a linear map, but what it is not is that it's not a unitary map, because what you're essentially doing is that you're applying a unitary and then applying this post-selection map onto some like maximally entangled state. But at least applied to this like initial state, it's very clear by simply just bending this leg, what you end up getting is this picture that you see from the outside. And what's nice is that in various ways this is consistent with Hawking's assumptions. For example, you get like finite black hole entropy, and you get effective field degrees, effective field theory for both the interior and the exterior. And also you have the unitary of the left-west matrix. So to be clear, in this picture, everything is unitary. Insofar as you assume that this is a unitary process, what you get here is unitary, like by definition. But I'm going to argue that if you try to like add some realistic features into this model, it's not too obvious that this model would end up being unitary. And that's the issue that I want to discuss this talk.
So this seems like a generalization of the final state proposal in some ways.
Yes, that's right. Yeah.
And there was a distinction between the case where where the final state is sort of very carefully selected as opposed to just random. Can you comment on that? I mean, because if it's random, then you get an almost unitary answer on the outside, but not quite unitary.
So I think that this is not really a projection onto like a typical state, because for one thing, you have like an angled state between the left and the right side. Then you might argue that, oh, maybe you're applying some like typical like unitary on this side. And I don't think that's quite the case, because unitary is a scrambling unitary, but it's not a random unitary. From the outside, it looks like some efficient quantum process. So I think it's not quite a like a typical projection. Something more structured than that.
Why does it have to be scrambling but not random if it's like associated with just the map and not the...
Right, so it's scrambling but not random, because from the outside perspective, we have some quantum system that is evolving for some time, and we expect the complexity of that unitary to be not like exponentially complex. So if you have a random unitary, the complexity with high probability would be exponentially complex. So that's why we don't expect it to be actually random.
But I thought thought U was just the holographic map and not necessarily associated with the black hole evolution. Is that?
Could be, but like if you accept, we could say that U is some unitary, and whatever it is, like once you apply this map from the outside, you see this. So
Gotcha.
yeah, I think the reasonable thing to assume is that this is like a black hole evaporation.
How do you think of the AMS protocol in this picture? So if
Right.
I extract the purification of a late outgoing Hawking quantum and jump in with it, then it would be inconsistent for me to see a smooth horizon, at least in that mode, right?
So in the AMS protocol, what would you do? So you would like first do something with this big R, and then you move in, and then you're trying to see a violation.
So I would extract, I would aim to cross the horizon at a particular time, and I would pick a particular outgoing Hawking quantum that's already in the semi-classical regime, but near the horizon, and then jump into the purification or new purification of that quantum, which is guaranteed to exist by unitarity.
Right. Well, at least in this effective picture, I don't see. Let's see.
So I think that the answer that, at least when I talked to the authors of this paper about it, their answer would be that then there is no effective picture. So that the effective theory breaks down and that it's valid only. So I think that, I mean, one way of phrasing this is that the challenge is really to see how much this tells you if you want to go in the other direction. The fundamental theory gives you some state of the black hole in the exterior, and you want to predict what somebody's going to see when they cross the horizon. And I think what they say is, if there is a simple effective theory state that maps to the fundamental state that you start with, then that's the one.
Right.
And it's going to be unique. And if there isn't, then I don't know.
Yeah, I believe like you're like to be clear, this is really a map from like a family of states to a family of states. So even though it looks like you have some like general like particular fixed input state, and yeah, I believe what they're saying is that you need to only consider like the sub-exponentially complex state in the effective picture. Otherwise, you don't get this like unique map to the from the outside point of view. I feel like the process of like extracting some mode in the interior by probing this like big R, I feel like that's not like a sub-exponentially complex operation.
And that's fine, but of course it's problematic. I mean, this is not your problem. We shouldn't maybe spend much time on it, but it's problematic because if you say the effective theory breaks down if you extract this purification, but not otherwise, then you also have to do multiple things. You have to fill this in with a rule for what the state of the horizon is for any state on the outside. And moreover, it's not clear when you're supposed to look at the state on the outside, but I could re-encode the purification into the Hawking radiation by reversing the distillation unitary. And I could go back and forth as many times as I like, and so there's a world line of radiation, like at which point I'm supposed to cut it and look at the state and say that determines what the following observer sees. So it's not clear to me that, well, it seems pretty clear to me that their model cannot be turned into a resolution of the firewall paradigm.
Let's see. Other comments? Yeah.
Can I ask you a question? What is phi naught here? Is that the state of quantum fields inside the horizon?
I think it's some like initial condition that like eventually forms into a black hole. Like for our purpose, like it's this guy will just stay as like a placeholder. Like it won't really do much. But in this picture, well, you have like L and like psi naught, and then after that you form a black hole. So I would expect to be some,
I see. So what is L supposed to be then?
like the left moving universe, like in this picture, that falls into the falls in the radio universe.
see, so is that supposed to be the state of quantum fields in the black hole?
Not the, let's see.
I think L is just a label for the infalling. I mean, for the moving modes and
See, but I thought you were
state.
I thought all of this solved some problem where you had a Hilbert space that had too large of a dimensionality, and this map reduced the dimensionality of the Hilbert space. And I'm curious which subsystem that is that has the wrong dimensionality.
Well, the global system, right? Because it treats the black hole interior, never mind how you label it exactly, but it treats the black hole interior as independent of radiation.
And that corresponds to what subsystem here? Is it L or phi naught or?
LR and phi naught. Little r.
Little r. I thought little r were the interior Hawking partners.
Yeah, like the, I mean, it's moving in the opposite direction with L, but, yeah, it's still in the interior.
The thing about after the page time, right, there's already more, just a little r's, there's already more of them than the entropy of the black hole.
Right, okay, yeah.
Okay, so where's the issue? The issue can arise when you have interaction between the left and the right moving node, basically. And to be more specific, like you can like imagine like throwing something into the black hole from the outside, and this could be some programmed robot that like interacts with the like radiation outside, and it does something in the inside. For example, you apply this unitary U, and then you apply this like unitary V. I think this is a totally plausible thing that you could do. And so it's natural to ask that once you like throw in the robot, like do you still have unitarity? And are there any funny things happening? And I should note that this might sound like an academic problem, but you could actually, if you have like a quantum system, it's actually not that hard to check whether the process is unitary or not. What you can do is that there's this well-known test called like swap test. So that when you have like two like quantum states, you can like easily check their overlap. And the entire process, insofar as you can efficiently compare the state side 1 and state side 2, all you need to do is just apply this like conditional swap. And that's like a very easy operation. So in principle, what you could do is to compare two identical black holes, and you throw in identical robots, and you get like, and you get some state. And you can check whether you pass this swap test or not. So if it is unitary, then you pass this test. If it is not, then you get some like different answer. So there are like two questions that we were kind of worried about when we first looked at this proposal. One is that is the outcomes of this experiment actually consistent with unitarity? And secondly, you know, if you think about it from the outside point of view, all we did was to throw in some robot, and that shouldn't really change the fact really shouldn't change the complexity of the black hole operation in a significant way. But as I'm going to tell you soon, there are some worries which suggest that perhaps the complexity of the black hole operation may get extremely complicated, but just by like throwing into something, if you accept the non-isometric whole picture. So the key issue can be viewed as follows. So let's suppose we accept that this map is true, and we simply add in these like extra gates. And what I do is that I just added in those gates here. And after you just bend these legs in a way that we did before, the diagram that you get looks like this, which is no longer obvious if it is unitary or not. So the question is, for any like reasonable like a U and V that we can apply this way, is this like a composite linear map? Is that a unitary operation or not? And this issue, mostly in the context of the final state proposal, but like this issue still remains. was pointed out by Boyle and Prescott. The point was that if you look at these like unitaries, first of all, if you look at this red one, like even if you don't have U prime, you can see that the direction of one of these legs has changed. So that means that you are applying a partial transpose to a unitary. And whenever you apply in general, if you apply partial transpose to a unitary, the map that you get is generally not a unitary. So that's one concern. And the other concern is that from here and here, you can see that the order of the gates has changed actually. So even if somehow this like unitary V ends up being a unitary, like after applying partial transpose, V remains as a unitary, it's not obvious like what this actually means because it's like you have two unitaries and their order has been exchanged along like one particular leg. So, and another issue is that when you have post-selection, from the perspective of computational complexity, some like very weird things can happen. So it's been pointed out before, for example, by Boyd, that you can, for example, have a closed timeline curve if you have like post-selection. And in just like a purely complexity theoretic like context, if you have this like B2P, which is a class of problems that you can solve efficiently using a quantum computer, and you simply add in post-selection, then you get this like complexity class PP. What's important is that this includes like NP, for example, and we don't expect we don't expect to be able to solve like NP hard problems in a reasonable model of computation. So that's another concern. So really, post-selection really leads to like two potentially very exotic phenomena. One is the violation of the unitarity. Another is the potential blow to the complexity of the black hole S matrix. And this is what we want to discuss in this talk. And it turns out that the key to resolving, so long story short, it turns out that within this model, these problems actually do not arise, but in a non-trivial way. And the key to resolving these tensions is based on a concept called the pseudo-randomness due to G-song amplitude. So let me first talk about this pseudo-randomness, because maybe not everyone is familiar with it. So let me first talk about pseudo-random states. So these are a family of quantum states. You can think of it as like an ensemble of quantum states, which are not quite far random, in the sense that you can efficiently produce them. But nevertheless, for all intents and purposes, you will be unable to distinguish them from a far random ensemble. So the fact that such a state exists is somewhat surprising, but once you look at the construction, you can see that it's actually plausible that such a state exists. And the idea is the following. So you start with a uniform superposition state, and what you would do is that you would apply some like a pseudo-random phase. So imagine like you're in your computer, you have these like random number generators. Imagine like applying like random phases based on those like random number generators. And you know those numbers are not like truly random, right? They're like we just think it's like hard to distinguish them from like a truly random numbers. And the fact that you can prove is that if these are like a truly uniform random, then information theoretically speaking, the resulting family is indistinguishable from like car random ensemble, as long as you have only like polynomially many copies. Then the argument is the following. So let's say I apply these like pseudo-random phases, and if I have good reasons to believe that even a quantum computer cannot like distinguish these like pseudo-random numbers from like the true random numbers, and if you can somehow distinguish this state family from a hard random state, then you would run into a contradiction. Because if you do that, there's this like very concrete test in which you can distinguish the pseudo-random numbers from the truly random numbers. Basically, whatever this black box you have that can distinguish these family of states with the hard random states, just produce the states this way and then plug and put your quantum state into this black box. And that black box will be somehow able to tell whether these numbers will be pseudo-random or not. So that's a contradiction. So this is how you create pseudo-random quantum states. For the purpose of this talk, what we're going to need is something a little bit more complicated, which are called as like pseudo-random unitaries. And these are unitaries which are efficiently implementable. So you can implement all these, it's an ensemble of unitaries. Each of these are all efficiently implementable using only polynomial in any case. But if you try to distinguish this like unitary family from a Haar-random unitary, you just won't be able to do that. So it should be noted that the construction for the pseudorandom quantum states actually doesn't work here, because if you simply apply like a pseudorandom phase, and if you apply to like the basis states of the diagonal basis, like the computational basis, you're just going to get some like a computational basis state times some like a phase. And that's like clearly distinguishable from what you would get when you apply a like a Haar-random state, right? So this doesn't quite do the job. You need a more complicated construction. Yeah.
So for the computational indistinguishability of the unitary, that would be like with poly and copies of you and the same fixed state, or like is there any?
Right. So you have like a poly and like copies of you, and you're allowed to like plug in like any like input state as long as it's like polynomially complex, and you're allowed to like measure in any basis after that as long as you like have like if that measuring basis is only polynomially complex. And against all those tests, you won't be able to distinguish what the measurement statistics from the measurement statistics that you get when you place these unitaries by Haar-random unitaries.
Are these unitary k-designs?
These are not quite unitary k-designs because it's like weaker. So if you have unitary k-designs, even if your like measurement basis is exponentially complex, you will not be able to distinguish the two. But here you're merely saying that if you restrict yourself to polynomially complex measurement basis, then you won't be able to distinguish the two. So in particular, you may, it could be that you know, there's some like certain amount of entropy that you need to produce like a k-designs, because you just need enough number of states to get the ensemble. It could be that you need just a drastically lower number of states, drastically lower number of unitaries, and still pass this test. That said, I should say constructing pseudorandom unitary family is like a topic of like ongoing investigation. Like a lot of people are thinking about it, but there's basically nothing is known about this. There's some like plausible constructions. For example, if you have like pseudorandom bases in like two complementary bases, and if you like alternate like this, like let's say many times, I think it's plausible that you can get like a pseudorandom unitary, but nobody was able to show this. Another plausible candidate is that maybe you apply a random quantum circuit and you just trace out like some like small portion of the circuit, and it's possible to expect that the channel that you get is like very close to the channel produced by like a Haar-random unitary, if you only allow like polynomial complex operations. Again, this is not known. For the purpose of this talk, though, I will need to make some assumption, otherwise I can't do anything. And the assumption morally is the following. So remember, U prime is, what is this? So this is a unitary this is a unitary describes a black void operation. So you start with some like initial state, and then you throw in a row of I, so I is the involver. And after you do that, imagine like tracing out B, which is the black hole. So I only have access to radiation. And my claim is, our assumption is that if you replace this U prime by like Haar-random, you won't be able to distinguish the two, as long as you only allow like a polynomial complex operations. So that's an important assumption. Maybe I should pause here, and if there's any questions, this is a good time to ask actually.
What was U prime originally?
So why is U prime? So like if you don't have the involver, I just wrote down U, and just to make sure that it's not exactly the same unitary, I wrote down as U prime. But it's still the unitary that describes the evaporation just with the involver.
So before it wasn't Haar-random, and now U prime is Haar-random?
No, I'm not saying that. I'm just saying that U prime is some unitary, and suppose you trace out B, okay? And suppose I have a Haar-random unitary, let's say V, okay? And applied to the same subsystems, and I also trace out B. I'm just saying that computationally speaking, you won't be able to distinguish the two. That's the assumption. I'm not quite saying that you climb is like hard random. Alright, so assuming that you accept the validity of this assumption, well, I'm going to claim that with good precision, unitarity holds, like not exactly, but like with a pretty small error. Let me remind you that the pertinent question was this. So if you have an info on a robot that interacts with the mode outside and the inside radiation, upon like straightening the legs, the diagram that you get is a linear map, which is here. And the question is this process unitary? No matter how you choose, like U and V. One thing that I should note is that if you're allowed to do anything, like in your choice of U and V, in general, unitarity will not hold. So here's an easy example to see that. So like consider this like a simple like process, which is a swapping like two qubits like A and B. And upon like applying a partial transpose, what you get is this like input is like projection. So what it does is that no matter what input you have, you project onto the EPR state and out comes the EPR state. So clearly this is not a unitary operation. And the idea is that like one thing that you could do, for example, is that you could just like decode a radiation to see what's inside a black hole and apply like a partial transpose on like part of line, effectively reproducing this. And obviously, we don't really expect to be able to do this, but the point is that there needs to be some condition in order to ensure that you have unitarity. Otherwise, you can run into these weird counterexamples. And if you have a R-random unitary, even though the unitary that we have is non-R-random, if you like somehow average over these R-random unitaries, what you can get is that you actually get like exactly a unitary process on average. And moreover, the fluctuation is exponentially small in the initial black quantity. And this is already like very similar to the calculation that was done by Akers et al. So this part is not new. But the key question is, so clearly, if somehow our result, this is our original setup, can be reduced to this like integrated version of our random unitaries, then we're going to get like the result that we wanted, which is at least like approximate unitarity, and that's what I want to show. So. If you look at it, like you might say, oh, like I already said that like U prime will be like indistinguishable from like R-random unitaries, and as such, why does this just hold? And I think that's a valid point. But and in the end, it's not incorrect. But I should say that this is not obvious either. And the reason is that when we say that unitary U prime is indistinguishable from a R-random unitary, what we really mean is that if we have like a polynomial complex input state and a polynomial complex like measurement, then we won't be able to distinguish the two. But you can see that here the operations that we're applying are not really just unitary operations. These are like in general non-unitary operations. So we should really argue that even if you're allowed with these like, even if you're equipped with these like non-unitary operations, you still will not be able to distinguish this U prime from the R-random unitaries. So that's the challenge. So the obvious thing that you may want to try is to simply like straighten the leg so that like things become actually unitary. And so let me remind you that even though we had this diagram, prior to like writing down this diagram, what we had was a purely unitary process in the effective picture. Then we applied some like a non-isometric map, which is essentially unitary followed by pole selection. So just like rewrote that like again. It's the same diagram. Yeah.
Can I ask you a question that probably shows that I'm making something basic, which is that I thought that the sort of key result in their paper was that they had shown that so long as you restrict to a set of simple effective states, that they could be effectively distinguished in the exterior, so there are small, exponentially small overlaps between the images, but so long as you don't allow arbitrary superpositions of these states, they're actually distinguishable in the image of the map. Well, to what extent are your results a consequence of that? I mean, doesn't that have to be true because the operations, the red and blue operations that you're performing aren't they simple in their sense?
They are simple, but there's an issue, which is that when you look at this post-selecting map, like it is being applied to a potentially huge system. So like let's imagine you're like past the page time, like well past the page time, so that you can like the R is like much larger than like B, for example.
Sure, but that was true in their analysis as well.
Right. Yeah. I mean, I would say let's see. I think there's a difference in the assumption. So what did they do? So they did some calculation based on like the hard random unitaries, and there was an argument that for like certain class of unitaries that they considered this argument, like the result that they got from the hard random unitary, will be approximately consistent with that. Here, like we're being a little bit more explicit about the assumption, which is it's really assumption about the unitary about the black hole evaporation. So I would say I'm pretty sure the assumption that they made and the assumption that we made is not exactly the same. And I would say we're trying to start with this assumption, which I think is more physically motivated, and then try to derive everything from there.
So you're able to get this result from a much weaker assumption.
I think so. I think so. Okay, so this is good. So this is the original setup, and what's nice about that is that except for this like final stage, everything is unitary. But as I said before, the post-selection is applied on a huge system, and this is gonna lead to some problems. So what I want to advocate is this identity. So this is an exact identity. The left-hand side and the right-hand side are exactly the same. What you should do is to, you see this like big R here, you should move that by all the way over here, and you should like bend this I in this fashion. Okay. And after that, you get this. I hope everyone is convinced. And if you accept that this identity is correct, now on the right-hand side, what you have is something that, in my opinion, is better, which is that you're still doing something non-unitary, but the thing that you're post-selecting on is no longer a huge system. It's like a small system involving only the observer. Basically, I is the infaller, and I2 is some auxiliary system that we introduced for the sake of making the circuit unitary. So this is much smaller than R. So if you just make the broad, imagine this is like the broad version, and just make the broad and ket version to make it like a density matrix. And what you get is just simply this. Okay? And here's the key point. So right now, what do we have here? So we have some unitary. We start from like quantum states, and we're applying some unitaries, and we're applying some like measurement here. Now here, it used to be a post-selection in the previous slide, but here, like we're asking, if I measure in this basis, what is the measurement statistics in that basis? Okay. And by our assumption about the pseudo-randomness of U prime, we can replace this entire tensor network into a version in which U prime is exchanged to this should be the average over R random unitaries. And so it should be like an average over the version in which U prime is replaced by V. into like a fundamental unitary. And there, now you can just do the averaging like explicitly, and that on the right hand side to get the result. And that turns out to be 1 over I squared. The key question is, what is the error? For these like pseudo-random unitaries, the error basically is determined by the part that is being traced out, which in this case is the B. And we expect this error to be superpolynomially small, and basically the number of qubits in this subsystem B. So that would be the error between the left-hand side and the right-hand side. So collecting everything together, what we see is that coming back to this like linear but potentially non-unitary map, the deviation from unitarity is essentially determined by the dimension of the infollower square times this like a small error, which is determined by the size of the remaining black hole. So if we were to carry out the same analysis in which we didn't make this transition from post-selecting on the radiation to the post-selection on the infollower, we would have gotten something like R squared here, which would have been like a much larger number. So that's why like making this transition to the post-selection on the infollower was very important. So the moral of the story is that no matter how you choose this UNP to be, as long as you're polynomially complex, you get something very close to unitarity. So is that satisfactory or not? I'm not sure. Like I understand that people want like exact unitarity, and we don't quite get that. But our thought is that the deviation from unitarity is like exponentially small in the size of the remaining black hole. So if there's some like quantum gravity effect, which is like exponentially small in the size of the remaining black hole, perhaps like you can compensate for this effect. That's just a speculation.
I don't think that they meant to define the fundamental theory in this way. I think
right. So
that's why they wouldn't lose any sleep over this slight failure of unitarity.
Right. So I guess like they just didn't deal with the interaction. So in principle, if you were to modify their picture for the case in which you have an interaction, perhaps our modification is incorrect. So that's one potential criticism.
I don't mean to criticize what you're doing. I'm just saying that even in their simple model, without any interactions, you would still find that I think they chose a final state where you don't have exact unitarity. You have some exponentially small errors in the exterior, and I think their point of view on this is that the role of this non-isometric map wasn't to say it defines the actual fundamental theory from an effective theory. It was meant to go in the other direction.
I see what you mean, but
yeah.
I think the unitarity is about like two different things. I think like what you're talking about is like the unitarity when you consider a map from this effective picture to the fundamental picture. But here,
no, I meant the unitarity of the scattering matrix.
Also the scattering matrix, but in their model, the scattering matrix will be just like unitary, like manifestly, because you don't have these like extra like B-deckers, right?
Yeah, but I think the way the non-isometric map is defined, it doesn't necessarily give you exactly a unitary matrix in the exterior.
In the absence of interaction, they have exact unitary.
Well, yeah, let's check it out. My recollection is that they chose a random state for the final state.
So, right, so that's the conclusion. At least, if you accept the pseudo-randomness condition of the U prime, then what you get is an approximate unitarity for the Hessian matrix. Okay, and let me move on to this other topic. So the concern here was the following. So generally in like quantum computing, if you allow post-selection, the complexity tends to like increase quite drastically. And it seems like if post-selection is like a fundamental part of this like a black hole map from the effective picture to the fundamental picture, even if you do something simple in the effective picture, that might translate upon post-selection in the fundamental picture to something potentially very complicated. And that's like a kind of worse. Because from the outside perspective, all we did was that we threw in some like robot into the black hole. And I think it's possible that that shouldn't change the complexity by too much. So yeah, that's the question. Yeah, is the complexity going to be like exponentially complex? But then it's not totally obvious because again, if we just look at this picture, we're post-selecting on a huge system, and generally that translates in quantum computing. That translates into the possibility of like amplifying like a computational outcome which has like a super small probability of success, like a drastically larger probability of success, and that's. That would be kind of problematic. So this is a picture. So you see like PP here and PQP is here, and this is like a strict inclusion. This is expected to be a strict inclusion, and particularly this should include like NP. So yeah, again, at the end of the day, we get a result which is somewhat satisfactory, not completely satisfactory, but like somewhat reasonable. And what we can show is that the complexity of this map, in terms of like the number of gates that you're going to need, can be upper bounded by dimension of the observer, dimension of the involver, times the complexity of, let's say, U prime, like B and D. So if the involver is like very small, then like you don't get like dramatic increase in the complexity. That said, it's not very satisfactory because it could be that the involver is just it has number of qubits which is like a square root of the black hole entropy, right? So that's a possibility. It'd be still like much smaller compared to the size of the black hole, but in that case you get exponential of like a square root of the black hole entropy, which seems like a very fastly like increasing thing. So we don't know like how to deal with what's happening here. And the basic idea is this like well-known procedure called like an amplitude amplification, or specifically like a very souped-up version of it. And what it does is the following. So suppose we're given some unitary such that apply to some like simple state, like all zero state. We get some state with some probability. We get a state that we want, let's say psi, with a probability p, and some state that we do not want with a probability 1 minus p. And what this procedure allows us to do is to sort of boost this amplitude all the way to like a 1, provided that you have an ability to unambiguously distinguish the sign and sign perpendicular. And I suppose the basic idea is that we have this like a non-unitary process based on some like measurement, based on pole selection, and we can like boost that like a non-unitary process into like a almost unitary process with like unit success probability. And in recent years, there has been a big development in quantum algorithms that like kind of improves this like amplitude amplification in a very significant way. And this is known as the quantum like singular value transformation. What it does is basically the following. So suppose you have some unitary and projectors, and you can construct some matrix this way. And unitary, like think of unitary as like a sequence of gates that you're going to apply on a quantum computer, and think of projectors, let's say pi prime, as like your initial state on your quantum computer, and pi as your like measurement basis. So what this is morally representing is that you're starting with some like particular input state, like particular fixed state, and you apply some unitary on this fixed state times some like express system, and then you're performing some measurement. And if you've got the correct measurement outcome, then you know that you have applied this matrix A to your system. Obviously, that won't be a very deterministic process, but what this algorithm allows us to do is to make that like almost deterministic, meaning that if you want like to apply it with like probability 1 minus epsilon, you can do that with like a cost that scales like log, like 1 over epsilon. And how this works is very simple. So that's the model. So you have this unitary and like a pi and pi prime. an ability to distinguish whether you prepare the state or you prepare a state that is like orthogonal to that state. And once you have the ability, quite remarkably, for any polynomial, you can apply this like f of a side, like even though like this a is not a unitary matrix, and f of x is just like arbitrary polynomial with some like norm constraint, but essentially like anything that you can imagine. And basically, the complexity of this operation is determined by the degree of the polynomial. So the idea then is that if you want to apply some function that you want to apply, so let's say like a step function of some input matrix A, and what you would do is that you would approximate a step function by like a low degree polynomial, and like the higher you make the degree, you get like closer and closer to like step function, but you pay in terms of complexity. So what you do is that you like look at the like maximum error that you want to tolerate and find like the lowest possible degree that can guarantee that kind of error. So this is like a very general framework, and apply it to our setup. All we need to do is to just figure out what this like projector pi prime, and what this like unitary u is, so that we can make this non-unitary process a unitary process. So again, we have these two different choices, but I'm going to argue that this like latter choice is useful for us because we're co-selecting on this like small subsystem. And the choice is very simple. So what we do is that this pi, this just amounts to choosing our like initial states. So projectors onto these initial states, assign on f, and like a maximum integral state between I1 and I2. And what about pi prime? That's just like corresponds to the measurement that we're doing. So that corresponds to the projector onto this like maximum integral state between I2 and pi. And whatever is left behind, like the remainder of this circuit, like u, v, and u prime, that constitutes this like a unitary. So the easy calculus that you can do is that once you do this calculation, what you get is a some normalization factor times the post-selected operation, the operation that we actually want, with some like jump that we don't actually care about so much. So what we want to do is to change this like 1 over I into like 1 essentially to make this process like a unitary process. And to do that, there's a very normal way to approximate a step function. It turns out that this basically the optimal answer is no, and this can be approximated, the step function can be approximated by a polynomial of a certain degree, which is just proportional to this like I essentially. So after all that, what we can see is that this process can be applied almost deterministically with a cost that is proportional to the degree of the polynomial, which is like proportional to the dimension of the informer. So the overall, the cost is all the unitaries that are used here, called like C, times this like degree, which is like essentially pi. So for like a small enough like observer, the complexity doesn't blow up so much, but there is still a question of what happens if the observer, like the informer, is fairly large, like still smaller than the black entropy, but like no longer like order 1. So for that, like we don't have much of an answer. Okay, so the conclusion is that I hope I was able to convince you that this non-isometric code is very interesting, but it's not obvious if certain features that we expect to hold, such as unitarity and not blowing up of the complexity of the black hole evaporation, can be guaranteed in this model. And I think the crucial ingredient to resolve this like pseudo-happiness, and which certainly allow us to like restore unitarity up to like good accuracy, and restore the complexity, the reasonable complexity for the black hole evaporation, although with like less success. And what I find really interesting is that this is the only instance that I know of in which the post selection does not lead to any like radical modification of like known physics. So in particular, I was like very worried about the possibility of producing something like exponentially complex by like throwing something into the black hole. And I find it kind of amazing that somehow this problem is averted in this particular setup. So I'm wondering, like more generally, like if post-selection is allowed, like what is the limit? Like that's like something that I find very interesting. And one thing that is bugging me is that the complexity of this, like associated to the involver, was like multiplicative. But I would expect that like a more reasonable thing to expect is that the complexity contribution from the involver should be probably just like additive, not like multiplicative. But I'm not sure. It certainly seems like the existing ideas in quantum algorithms are like insufficient to like get bound like that. So perhaps to get better to understand that. And I should also mention that there's this like a very recent different proposal. I didn't have much time to go through it in great detail, but it'd be also interesting to compare it to that proposal. Okay, thanks for listening.